All right, teachers, how are you today? I hope you're watching this. I believe I had these videos set where um, they will mark that you have watched them. They should be helpful. They will help you with hopefully your tests and stuff like that too, not just your homework, but your tests. Hope everything's going good. Again, it's one of those things. Um, Teaching wise, I'll give you my little quick story where you got lots of things to do. Nothing like COVID to put a kick in all your old plans and stuff like that, and everything changing. If you don't like change, go be a teacher. So teaching changes all the time, especially this year. So, I mean, we're looking at when organized goes face to face, we're looking at probably our whole schedule changing, which means we got to change our meeting things, we got to change all our other things that we do with some of the kids that don't come to school. So it's going to be interesting. All right, so why don't we go ahead and get into 9.4? We're finishing up chapter 9 here. So let's go ahead and get into that. All right, so I'm going to start this up here. We are sharing, I hope. And I'm going to start this presentation. Illustrate. There we go. All right, so here is our share that we got. So we are finishing chapter on probability. We're going to be talking about the fundamental counting principle, permutations of like objects, and combinations. So one of the big things that gives a lot of students difficulty at is this idea of permutations compared to combinations. Okay, we do more permutations, but to give you an idea of how you tell the difference. Suppose you are in an ice. Let's say you're in Baskin Robbins, 31 flavors. All right, so you got 31 to choose from. But let's just say you want three scoops. The difference between permutations and combinations is that in a permutation, you would want your 3 scoops of ice cream in a particular order. Okay? You want 3 different flavors, but you want them in a particular order. Okay? In a combination, it doesn't matter what order they are, it would satisfy you. Okay? Put in another term, take the lottery. In the lottery, you pick 6 numbers to win. Okay? However, when you do that, it doesn't matter what order they come in for you to win. Okay? So in that case, it is a combination. Okay? If it was a permutation, it would be even harder to win because you have to get the 6 numbers in a row. All right, so that would make it a lot tougher even for those standards. All right, so permutation, arrangement of things in a definite order with no repetitions. Okay, in other words, you have a certain order, that order matters. You want to have anything repeat because if it repeats, it's the same order, so it doesn't count twice. Okay? Have this permutation. We'll kind of do some others. Fundamental counting principle. Okay, the fundamental counting principle. Let's go back to Baskin-Robbins. If you wanted to know how many different combinations of ice cream there are in Baskin-Robbins, you would take the 31 flavors. Okay, you have to take that. Okay, so you have 31 options there, and say you have 3 or 4. Say you have 3 different types of cones. So if you wanted, let's just kind of write that out for a second. I'm making that up by ear, but all right. So you have Baskin Robbins 31 flavors. You want 1 cone, 1 scoop on a certain type of cone. Let's say there are 3 types of cones. Okay, so that one scoop and 3 types of components, to figure out how many different ways that can happen, the fundamental property principle says you multiply those. So you could design technically 93 different orders of 1 scoop ice cream on 3 different cups. Okay? So that gives you an idea of what the fundamental principle is. All right, a factorial. A factorial is a shortened way to show something multiplied and its numbers going down. You start at the value of n, the next number you would multiply would be n minus 1, and then n minus 2, and then n minus 3, all the way down to you get 3, 2, 1. So the whole essence of that is, let's say you start at 7. 7 factorial, that's this exclamation mark, that's the factorial, means 7 times 7 minus 1 is 6 times 7 minus 2 is 5. It just goes down times 4 times 3 times 2 times 1. So you notice the 1, the 2, and the 3. These are all the numbers in between. So what you would do is you would multiply all those together and you get a value. Okay? So you can do that on a calculator. Remember, you can use any calculator in class. Most calculators have a factorial button. If you have a calculator and you don't know what a factorial button is, you might want to Google your calculator, take a picture of it. I might be able to find it for you too and send it to me. Either way would work. Okay? All right. Oops, I need to get out of that. All right. All right, permutations of an objects in a set. The number of permutations are of our objects chosen in a set of n objects. We have a group of objects and we're choosing so many out of that group. So R has to be less than n because you can't take more things than n. Is denoted by n numbers, permutation of n numbers taken R at a time. Okay? Now, how does this work? And you have this formula. Now, this is a formula you're probably going to write down. I'm going to try and figure a way to see if I can make sure I give you this formula for that test question, or I may have both the formulas for permutation combinations, and you just have to know which one to use. So any of those might work. And I'll figure out how I'm going to do that. But some way you're going to have the formulas. Okay? But you need to know how to use it. So if you have, let's take that 31 ice creams again. There's 31 ice creams. And we're going to make 2 scoops of ice cream. That would be a permutation of 31 scoops, taking 2 at a time. We don't know how many different options we have. So there's a shortcut to this, but this means by this formula would be the n, 31, would be 31 factorial over 31 minus the 2 factorial. Okay, which would be 31 factorial all over 29 factorial. Now, here's the shortcut. This would be 31 times 30 times 29, oops, that's a 9, times 28, and it'll go all the way down until 1. All over 29, 28, all the way down to 1. Okay? Now, seems simple, right? It seems like you got to multiply all those numbers. Okay? Well, that kind of sucks because you don't want to drop it. That's a huge number. But think of it this way. When this 29 cross out with this 29 and this 28 cross out with this 28 and so forth all the way down to the 1. So in essence, all you have to do is multiply these 2 numbers. And so what you have is, it looks like 930 different options. Okay, so what I tell people to do is the bottom number is 29, right? So just write 31 times 30 times, and since I already know the bottom number is 29 factorial, and then the next number is going to be 29 factorial. And those cancel out, and so all you gotta do is multiply those two. Okay? Easiest way I can explain it to you that I know of. Okay? So that is how we do permutations. All right, so it says baseball team has 9 players. Find the number of ways the manager can arrange this. Okay? So they 9 players, you have to play 9 at a time. So that's basically, if you're using all of them, you're using all 31 of the flavors, you'd have to multiply. That's going to be your fundamental counting principle, okay? Which is going to be 9 times 8 times 7 times 6 times 4, and you multiply. In other words, 9 factorial. So there is 362,800 ways he can make his lineup. Okay? Find the number of ways of choosing 3 initials from an alphabet if none of the letters can be repeated. Couple of key words here. The key words are you're choosing 3 at a time out of the alphabet. The alphabet's got 26 letters, right? And the letters, none of the letters can be repeated. That's key. That makes it a permutation. So that is going to actually make it the permutation. So it's going to be 26p3, which is 26 factorial over 23. That's the 26 minus 3. And then notice they do it the same way. You cross out the 23s, and you're good to go. And you find out that there are 15,600 ways to do that. Okay? Now, FYI. Okay, let me see here. FYI, real quick. There are some calculators, graphic calculators, that if you learn and use your Google or YouTube it, ask them how to do a permutation on your type of calculator, it will actually do this work for you. So that's just an FYI for you. Why calculators are okay. And I don't care about that as long as you know how to set it up. You may have to know how to set it up. All right, permutation involving like objects. Okay, if you have n objects in which R1 and R alike are alike, R2 are alike, and so forth, you can figure out how many permutations. Because if you have like numbers, if order matters, you have to figure out how many of them you have left, basically. Okay, easier way to show it is this. Find the number of arrangements of the letters in each of the following words. Now notice, you have some letters that are repeating. The B represents, there's 3 of them, correct? Down here, statistics, S, 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 D, D, T, I, and I are all repeat letters, okay? So that's going to make a difference as we go on. So let's look at the next one. So how do we figure this out? Well, how many letters are there? There are 6 letters. That's 6 factorial. But 3 of them are repeating, so it's actually 6 factorial over 3 factorial. Okay, because the repeating will cut down on some of the permutations. And so 6, 5, 4, 3 to the factorial, those cancel out, gives you 120 different ways to arrange those letters. Okay, statistics, there are 10 letters. There are 3 S's, 3 T's, and 2 I's. So it's 10 factorial, and then 3 factorial, 3 factorial, and 2 factorial. And if you don't happen to have a calculator, there is a shortcut to that. Okay, you can multiply this out. Okay, so I would take out the big numbers first, like this 3 and this 3 would take out the 9. Okay, and then I would take out, let's see, the 2, and the 2 is 2 times 2 is 4 times 2 is 8. So I take out the 8. So now all you have to do is multiply these numbers together and then multiply it times 10, and you get 50,000 different ways rearrange the letters. Okay, and what happens is you take out some of those space. Otherwise, it's not permutation. All right, combination. An arrangement of objects in which the order makes no difference. Okay, so like the lotto, if you get it in whatever order, you still win. Okay, your ice cream cone doesn't matter what order the ice cream. So the number of combinations of R chosen out of the n. Okay, so how do I find this? Look at this. Here's the formula for combination. Combination taken n at a time is the same as the permutation taken n r at a time all over p permutations of r taken r at a time. Now, FYI, any permutation, if this letter is the same as this letter, it is basically that letter for that number factorial. Okay? So notice this is the definition of permutations taken in at a time all over r factorial, which is this here. Okay? And so it goes through all of this stuff. Okay? They actually take this, comes down to here. And so you can actually use this as your formula for combinations. This is a good one to know. Okay, if you know this one, you'll be able to handle it because this is just n factorial over r factorial times n minus r factorial. That's the one you want to know. That's the safe one. Okay. All right. So the library of science book offers three free books from less than 42. How many possible combinations? Now, what makes this a combination? Because it doesn't matter which order you get the 3 books in, it's still going to count. Whether I get book A, B, and C, or they give it to me as C, A, and B, I still got the same 3 books. And that's all that matters. Order is not important, so it is a combination. There are 42 ways to get the first book, 41 ways to get the second book, and 40 ways to get the next book. There are 3 circle numbers that can be arranged. Okay? 3, 2, 1. So 42 things taken 3 at a time is going to be 42 factorial by that rule over 3 factorial, which is this number, and then the subtraction of the 2 is this number. So you can go 42, 41, 40, and then 39 factorial would break up into this 30 factorial. Oops, you need that, okay? And so it just works itself out. Okay, in fact, okay, so it's missing a piece. I don't know why they didn't put that in. All right, so this would still be 39 factorial. That cancels out with that one. And this 6 would cancel out with this 42, gives you 7. So 7 times 41 times 40, that's gone, is this number here. And that's how you would, if you didn't have a calculator. Now, if you have a graphing calculator, there's a way you can put this in your graphing calculator. In a lot of calculators that have combinations. Again, Google if you do have one of those. It'll help you. All right. Now, at the beginning of the first semester, mathematics class for elementary school teachers, each of the classes, 25 students, shook hands with one another. Okay? So, with each other only once. How many handshakes took place? You have 25 students taking 2 at a time because 2 people shake each hand at one time. And so there's 300 different ways to make that happen. Since the handshakes between persons A and B is the same as the person between persons B and A, like if I shake your hand, you shake my hand, that counts as 1. Okay, this is a problem of choosing combinations of 25 people 2 at a time. Okay, Now, given a class of 12 girls and 10 boys, answer the following. In how many ways can a committee of 5 consisting of 3 girls and 2 boys be chosen? There's 2 different groups of people. Okay, so what you have to do is you're going to have to find. In a committee, it doesn't matter. Whoops. In a committee, it doesn't matter the order of the committee. If you're on the committee, you're on the committee. If it was you're choosing a president, vice president, and secretary, then order matters. Okay, but because you're not specifying the positions, it doesn't matter. If you're on the committee, you're on the committee. So you first have to find how many girls can be chosen, which is 12 girls out of 3. Picking 3 girls out of the group of 12. You also have to find the boys, 10 boys, and taking 2 at a time in a combination. And what you're going to use is the fundamental counting principle, which says take the combination of the girls, figure that number, take the combination of the boys, figure that number, and then multiply the 2. And this is kind of done the shortcut way. Okay? And then you can, this again just crosses out certain things. Okay? And this, they kind of shorten this one out. Use the formula to do those. Okay? And then the only difference to finding the probability of the combination is once you find the combination, here's the combination of what we were talking about. Okay, same problem. To figure out the combination or the probability of those happening, okay, way back in that, we know that there are 9,900 ways to choose 3 girls and 2 boys. So if I want to, it says here, since you know there's 3 girls and 2 boys chance, you take the 99,000 or 100, excuse me, and divide it by this combination, and you get your probability. Now, this is one thing I'm not going to have you do. So you don't have to worry about. It's not on the test, but I just want to show you that one problem. Okay. All right. So that is the last part of that. Okay. So it took this number and then did one more combination. Okay. Find the committee of 5 people. Okay. And then out of the group of kids. Okay. All right. So I hope this helps. It is a difficult part, but I will tell you this: chapter 10. If you know how to read graphs, chapter 10 will be fun for you. Okay. Hope this helps. I'm gonna stop sharing for a second, and we will see you hopefully soon. Make sure you're watching the videos. It does track you when you do watch the videos. That is part of the things I need you to be doing. They are going to be helpful for you. Okay. All right. We will see you.